29th of June 2021. Thank you very much for Dr. Munzir for joining with us. And so the joining for Dr. Asnawi from Universitas Negeri Surabaya and Prof. Yasin, especially as the Dean. And so participation for all our students. Dr. Munzir, today there are two levels join with us, the bachelor student and magister student, especially in biophotonic lecture and biomedical photonics lecture. I am and Prof. Yasin as the lecture in this lecture, in two lectures. And so thank you very much for Dinda, okay. Amalia, okay. Thank you very much for participation of all of students today. And so for Dr. Munzir Abdullah, maybe you can have the 90 minutes for delivering your presentation today. And 3 minutes for the question and answer. Yeah. So before we can start our lecture, I hope Prof. Yasin give the opening speech as the Dean and as the lecturer in this lecture. Please stand for yours, Prof. Yasin.
Yes, thank you, Prof. Reno. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera bagi semua. First of all, thank you for Dr. Munzir. I can give talk to this morning with topic SPR and its application. Yeah. This is the second series of lecture. Now, Erlangga, our rector, is very happy because the rank in QS increased, yeah. From 521 become 465. Increase 59 points. SKS launching 8 June, yeah, 8 June. To next week lah about this rank. So Erlangga push faculty to invite research from foreign university like Dr. Munzir from USM. Erlangga focus collaboration with 100 until 300 rank like USM, UTM, UKM. Okay. Thank you, student. You can join this meeting. Yeah, I hope you can learn about SPR because SPR actually is new topic for us. We just learn. Prof. Retno initiate this topic for research in our department, so we can get new experience from Dr. Munzir. The task of the student to make summary, ya, Prof. Retno. Summary for this
result from this meeting.
Yeah. Yeah. Okay. Thank you, Dr. Munzir, for your time to give lecture for this morning. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Okay, we can continue with presentation, especially from Dr. Munzir. Are you ready, Doctor?
Alright, insyaAllah boleh.
Yes, okay.
Yep.
Okay. Time for yours, please deliver your presentation. Thank you very much.
Alright. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Before I want to start, I would like to thank the organizing committee for this DECOTA lecture, for inviting me for the second time. So this is actually my second time delivering the lecture, and the previous session is on, I believe, 1 month ago or 2 months ago, right? I don't remember. Maybe on April or in March. I forgot the date. By the way, my voice is it clear for all of you? My voice?
Yes.
All right, good.
It's clear. Yes.
All right. Thank you again for Dean of the FIS Unite for the opening ceremony just now, for inviting me. Today, the topic that was given to me actually is surface plasmon resonance. Me myself is actually I have limited experience on this also. I have limited experience on the surface plasmon resonance research, but I did some 1 or 2 projects related to this before. So with that little experience, I think I want to share with all of you. Maybe we can learn from one another based on these topics. And this topic is very interesting because if you check the number of publication in the surface plasmon resonance in the Web of Science, it increasing tremendously, increasing over the years, and that shows the importance of and the appropriateness of this technique as a biosensing application, especially. So without further ado, let me share my first slide. All right. Boleh nampak ya? Can you see the slide?
Okay.
Yes, clear.
Right. Okay. For those who don't know me, I'm Munzir bin Abdullah from the Institute of Nanoptoelectronics Research and Technology, USM. So we are located in the northern parts of Peninsula of Malaysia, in Pulau Pinang, it's an island. And we are the second oldest university in Malaysia. The first is UM. We are the second oldest university in Malaysia after UM. So this is the outline of the talk today. The first, we will discuss about the basic concept of surface plasmon resonance. This is important to understand the sensing capabilities of SPR. We need to understand what SPR really is. So we'll discuss about that in the first part of this talk. And secondly, we will talk about the fundamental behind how we use SPR or how we exploit SPR and LSPR, which is a localized phenomena of SPR for
perempatan, tapi nggak tahu lupa perempatan itu perempatan mana.
Iya, perempatan di itu loh.
Host, mohon Mbak Dinda.
Kayaknya sotonya enggak.
Please turn off your voice, Mbak Dinda. Host bisa di off kan, host? Minta tolong. Sorry, Dr. Mundir.
Okay, no problem. It's normal. All right. So that's the second part of the talk. The third, we will discuss about the overview of the SPR biosensor. Okay. All right. Can I continue now?
Okay.
Okay.
Dr. Mundir.
Right. So the third is the overview of the whole SPR biosensor. What is the types of the SPR? And fourth, we're going to go through about the different configuration of SPR and LSPR sensor. Next, we're going to talk about methodology of SPR signal acquisition, how the signal was signal acquisition will be taken, and also the application of SPR-based biosensor. And last but not least is about the summary of the whole topic. So by the way, this session, I hope that I'm okay if you want to interrupt me during any time while I'm talking. There's no problem. You can just ask me during my presentation or after the presentation. All right. So the surface plasmon resonance is a topic in nanobiophotonics. Okay, nanobiophotonics is a multidisciplinary field which relate to the use of light to image, probe, and manipulate biological material in nanometer scale. So we can see clearly we have three keywords in these topics in this field. First is nano, the second is bio, and the third is photonics. All right, there's three fields. That's why it is a multidisciplinary. So nano referring to the nanotechnology. When we talk about nanotechnology, we cannot. We need to talk about the plasmon, what is polariton, quantum confinement, all these terms in nanotechnology. And the second word is bio. This referring to biotechnology or biology. So we need to use this. We need to be familiarized with this term: analyte, binding partner, antigen, antibody interaction, and so on. And the third is photonics. All right, the third word is photonics. So in photonics, we have concept of photon itself. We need to know what is surface wave, evanescent wave, fiber optics or waveguide, adaptive optics, and so on. So this is actually the concept behind it is actually quite heavy because it consists of a lot of different disciplines. So the aim of nanobiophotonics is we want to use light, all right, to probe into the nanometer scale for biological application. So the problem for using light for this application is the biological material, the biological entity and biomolecule is very small, less than 100 nanometer, right? 100 nanometer. But the wavelength of light we know for visible is from 400 up to 600 something, right? Up to 700, you can say, nanometer. So the wavelength of the light itself is much longer than the biomolecules that we want to detect or we want to probe. So that's actually a problem of directly using light to probe into these biomolecules. So we need to do some modification. We need to exploit on very important properties of material at the nanoscale. That's why this nanotechnology comes in. All right. For me, myself, I think nanotechnology is very cool. I like the nanotechnology, and I like bio also, biology, biotechnology, and my field is photonics. So for me, this is way cooler than all of this because we have the combination of all of these disciplines. So nanobiophotonix. So it's very cool for me. Very interesting. All right. So what is SPR, surface plasmon resonance? SPR is actually about the color changing property of metal. So before we go deeper into the definition and the mechanism, the description of SPR is the color changing property of metal. So the metal, we know metal has a distinctive color. For example, gold, they have gold color, the gold hue that we are normal to. Right, and the color doesn't change. You do some working on that gold, the color will not change because of this is the intrinsic properties of bark gold, the color itself. So the SPR allow us to change the color of metal. All right. So when we talk about the color of metals, we need to understand two phenomena that involve during the light interaction with the target, with the metal target. The first is absorption. So the absorption is whatever the perceived color of the gold is actually the apparent color that consists of everything except for what is absorbed. So referring to the figure that I show here, show in the slide. So if we begin with the white light and we have the absorbing material, all right, for this case is metal, all right. So the apparent color or the perceived color is everything except for what is absorbed during the interaction with the material. So that is the concept of absorption. The second phenomena that can happen is scattering. So the scattering, based on the scattering process, the apparent color is what is scattered at the scattering medium. All right. So what is scattering medium? All right. So these two phenomena occur in metal. All right, in metal, but absorption in metal is limited. All right, because of the band gap, and we will discuss a little detail in, short after this. But in metal, we know the electrons are free electron, right? Based on the Drude models, of the in metals, the electrons in metal are free to move. It's a conduction electron because metal doesn't have band gap, so it can have any it can absorb any energy or photon that comes to it. So it can absorb. So it is free to move inside the surface of metal. Right? Unlike the semiconductor material, they have band gap, right? The band gap that the electron is not allowed to be inside the gap or to have that energy in between the energy gap. So we don't have that effect. The effect that we see in the gold, silver, and all these metals is actually because of the light that hits the metal, interact with the conduction electron in metal. All right, the conduction electron in metal, they reside or they occupy the surface area, the surface region of the metal. Because of the metal, the electric field in metal is zero. We know that. So therefore, the electron will occupy only the surface region of that metal. And that explains on why why metal has very little absorption invisible, mostly reflected because all of the light is being absorbed by the free electron, and the free electron after some time it will jump back into its original level, and in that process they re-emit the light. So whatever light that comes in, the electron absorb and they re-emit the light. So that's why all of the light, mostly all of the light is being reflected because very little absorption. So we have these electron on the surface of the region of the metal that I explained to you just now, and sometimes it is called sea of electron. All right, sea of electron, and because these electrons, they occupy the same position, they tend to oscillate in the same synchronized oscillation. All right, because of the same material, so it will oscillate in this in synchronized or coherent oscillation. So different metal has different work function, different ionization energy, and etc. that eventually determine the plasma oscillation frequency or Langmuir frequency. All right, so that's why we can see different, slightly different color of gold, silver, brass, copper, aluminum, and so on, because of different metal has different work function, and in the end they will have different plasma frequency. So basically, the electron on gold, the oscillation of the electron, the conduction electron in gold oscillates differently with the free electron that we have in silver, in brass, nickel, and so on. All right. But most of the metal have their plasma frequency at the UV range and shorter. So that's why most of metal, they reflect most of the light, and it only slight absorb. The absorption of the light is very low because of the plasma frequency of the electron is on the UV range for metals. All right, and that is also why metals appear shiny. Excuse me, I need to drink. All right, so let's continue. That is about the bulk metal, the color, why we have these different colors in the bulk metals. So what actually happens when light strikes the surface of metal? The answer is free electron respond to the oscillating electric field. We know the light is consists of EM, electromagnetic wave, and in EM we have the electric field and magnetic field. All right. So this electric field will induce response towards the free electron in the metal. And what will happen to this free electron is they will collectively or coherently or synchronously oscillate. Let me close this. All right. Okay, they will oscillate on the surface, and what comes out from this is excitation of a type of surface wave called surface plasmon polariton, or often called surface plasmon. All right, the real name or term is actually surface plasmon polariton, but often they just call surface plasmon without the polariton. So surface plasmon are coherent electron oscillation that exist at the interface, metal and dielectric interface. These are essentially light waves that are trapped on the surface because of their interaction with the free electron of the metal. But the electron oscillation decay exponentially into both material, and the decay length is about wavelength order. So we can illustrate this, or we can imagine this surface wave as this surface plasmon wave as a surface water wave. All right. For example, we have a drop of water hit the surface of water, and we know what will happen is the surface. We will have the ripples, the wave on the surface of water, and that surface water wave, they actually propagates along the interface between the water and air. Right. They spread like that. They propagate in that direction. So we can imagine that the same thing for SPP, surface plasmon polariton, whereby this time it is not a drop of water, it is a light that strikes the interface between the metal and dielectric, and the result of that is the excitation or the introduction of the surface plasmon polariton wave. All right. So this surface plasmon polariton wave is actually originates from the oscillation of the free electron. So when the free electron oscillates, it has very high energy, and we know the word we know plasma as the fourth state of matter. We have solid, we have liquid, we have gas, and the fourth state of matter is plasma. So plasma is in general is consists of charged particles. All right, the collective behavior of charged particle, it can be electron, it can be ion, it can be charged particles, and so on. But the collective behavior of that is called plasma. So that plasma also exists in the surface of metals, plasma. All right, and that the electron in the plasma, this actually oscillates at the synchronized oscillation frequency, and that synchronized oscillation frequency we can represent by the particle of plasmon. All right, plasmon. Plasma is the state of the matter that consists of the sea of electron just now, and the quantization of the oscillation of the electron is called plasmon. Sorry. So plasmon. So that's the word plasmon comes from. Okay, and we can say that the light that is introduced inside into the surface between the metal and dielectric is actually being converted into the surface plasmon polariton wave. So from the light, it be converted into the SPP wave. So we can directly imagine that if we have strong light, we excite the surface of metal with very high power of light, and then some of the optical power from the light is being converted into the SPP wave. What we expect is the intensity of the reflected light will be reduced because it has been converted into the SPP wave. All right, so that is basic understanding of the surface plasmon resonance. So we have talked about plasmon. Plasmon is the quantum of plasma. All right, plasma is the sea of conduction that I mentioned just now, and when it oscillates, it carries energy. That oscillation energy, the quantization of the oscillation energy is called plasmon. So now you might ask, what is plasmon polariton? All right, why we have this another particle, quasi-particle called polariton? So plasmon polariton is just actually another quasi-particle that is produced by strong coupling of photon with plasmon, right? So now what happened is we can have only plasmon, all right? But in this very case, the plasmon arises or produced with the excitation of photon. So from photon, it converted into the surface plasmon. So that's why we have a new particle, quasi-particle, plasmon polariton. So the third words that we need to discuss is the surface plasmon. Why it is called surface plasmon? Because it's actually a wave, all right, EM wave, longitudinal charge density wave along the metal dielectric interface. All right, so the basic concept is the wave, the surface plasmon wave will propagate along the interface between the metal and dielectric. So it's the same behavior with the surface water wave. It occurs on the surface only. All right. So back to the original, our original discussion, we want to change the color of metal, right? So how do we change the color of metal? The answer is shifting by shifting the plasma frequency. I told you about the plasma frequency in metal. Most of the plasma frequency in metal is in the UV. That's why most of the light is being reflected at the visible range. That's why it's very shiny. Metal is very shiny. But when we shift the plasma frequency from the UV range into the visible range, we will create absorption. All right, we will create absorption due to the plasma interaction with the light. And in the end, when we have absorption, like we discussed this now, when we have absorption, the apparent color or the apparent the perceived color is just whatever is not absorbed by the metal. All right. So how we can do this is we can use nanotechnology. So this is where nanotechnology comes in. So nanotechnology is the study of metals or materials in the size scale of 1 to 100 nanometer. Okay, so what we did is with nanotechnology is we reduce the size of metal from the bulk metal, for example, bulk gold. We reduce the size. What will happen is the plasma frequency will start to shift into the visible range. And okay, so the sea of electron I mentioned just now actually naturally oscillate inside the metallic nanoparticle. I'm referring to the figure here. All right. So if the light that is being introduced into the surface is not equal to the natural frequency of the metal nanoparticle, so therefore the oscillation is normal. This is a natural oscillation. All right. But if we supply the material or we shine the material a frequency that is similar to the plasma frequency or natural frequency of the nanosphere, well, we will end up with resonance. Right? We will end up with resonance. You can see from here the oscillation, the amplitude of the oscillation is increasing, increased because of the resonant condition. So the light that is the portion of the light that is similar to in terms of the value with the frequency of the resonant frequency will get absorbed, and that energy is being converted into this resonance oscillation, right? So the amplitude of the resonance will become higher, right, in terms of the amplitude of the oscillation. But this, I forgot to mention this sphere here, the negative sphere referring to the free electron, right? The free electron I mentioned is free to move, and the pink part behind it is actually the positive ion of metal. All right. So basically the nanosphere has been displaced the word is polarized. Okay, so the negative charge of the electron will move into one direction, and what will happen in the other direction is it become positively charged that consists of the ions. All right. So these positively charged ions will provide the restoring force due to the Coulomb interaction. So positive and negative, they will attract back the sea of electrons now. So what will happen is we have the oscillation like that, right? The natural the natural frequency with maybe this, like this, if you can see my finger. So at the resonant frequency, the light has been converted, has been absorbed by the sea of electron just now. All right, so what will happen is we have the resonant condition. And the Plasmon frequency can be calculated by using this equation that I show in the bottom part. So the Plasmon frequency is equal to n, which is the number of electron, multiple with the times the E, which is the charge of electron, divided by the mass of electron, and multiple with and times the permittivity of free space. All right. So in this equation, we can see E, M, and the permittivity of free space is a constant. So what is the only variable in here is actually the n, which is the number of electron. Since the number of electron in gold, in silver, in aluminum is different, so therefore the Plasmon frequency for each of these metal will be different, right? So Plasmon frequency will happen at different, the resonance will happen at different Plasmon frequency for different material. So gold have different resonant frequency, silver have different resonant frequency, and so on. All right, but the equation that I show you just now, the Plasmon frequency is actually the equation for the bulk metal. So if we have this bulk metal, we can calculate what is the Plasmon frequency. This is what I told you in the earlier slide, is the Plasmon frequency is in the UV range between 10 to 30 EV, right? But when we change this bulk metal into nanomaterials, we can make it into planar surface, for example. Okay, this planar surface of gold, for example. Okay, so what we have here in the table, the resonant condition change. All right, the resonant condition change because of the geometry has changed. Just now is a bulk material. We can imagine bulk big gold, but when you cut very thin slice of it, okay, with the thickness of a few tenths of nanometer, so we will end up with a planar surface. And in that case, the resonant condition change, right? And if we make the gold just now into a sphere with a nano, with a diameter of nanoscale, we are now with a nanosphere, and the resonant condition also change. And if you want to calculate what is the resonant frequency for bulk metal, is equal to the plasma frequency or Plasmon frequency. For the planar surface, thin film of gold, the resonant frequency is equal to the Plasmon frequency divided by square root of 2. For the nanosphere, the Plasmon frequency divided by square root of 3. All right, so the frequency will also change with a different geometry. So this is the nanotechnology part of it. The nanotechnology of part or concept behind the surface plasmon resonance. So in nanotechnology, we can produce two types of you can produce 0-dimension nanostructure. We can produce 1-dimension nanostructure. We can produce 2D nanostructure. We can also produce 3D nanostructure. But the one related to surface plasmon resonance is 0D and 2D, right? So 0D metallic nanostructure is actually referring to the sphere just now. This illustration and the sphere is actually a 0D nanostructure. 0D, D represent the dimension, okay? So 0-dimension metallic nanostructure. And it can also be in 2D metallic nanostructure. 2D means planar or thin film of gold or of metallic, of metal. All right. So as I mentioned, the resonant condition for these two material, two form or two geometry of metal will be different, right? Will be different. And but the important thing is the thickness or the diameter of the particle need to be much smaller than the wavelength of light. So the wavelength of light, we can say, for example, we take example of 500 nanometer of light, which is green or green to blue. All right, so this metallic nanostructure, the diameter is much less than 500 just now. It can be 10 nanometer, it can be 40 nanometer, all right, which is much smaller. So what will happen is actually the particle will occupy, can occupy the whole range of the wavelength, all right, that I show here, I draw here. this wavelength, I'm not sure whether I can draw. Let me try. All right. Okay, so this is the wavelength. And these two particles is actually much smaller than the wavelength. Okay, so the effect of that is this nanoparticle will experience the oscillation electric field, and we will end up with this current, the electron displacement or polarization. And what will happen is the oscillation will it will oscillate accordingly according to the electric field that has been introduced. But for the 2D metallic nanostructure, the thickness must be usually the thickness is less than the wavelength of light, right? For the SPR effect to be prominent, right? So if we begin with the 0D metallic nanostructure or nanosphere in this case, we will end up with a localized surface plasmon resonance. Remember the wave that I mentioned in the earlier slide about the surface plasmon wave. All right. So what happened is the photon, the light strikes the nanosphere, and it induces the surface plasmon wave. But because of the size is very small, this wave is actually not propagating. The wave in the surface of the nanosphere not propagating, it stays like that. So that's why we call it a localized SPR. So this is in short LSPR, localized surface plasmon resonance. If we use 2D metallic nanostructure, which is thin film of metal, we will have the same oscillation effect in the nanosphere. But now the surface plasmon will oscillate. No, the surface plasmon wave will propagate over the distance. All right, that's why we can see the contour here. Let me make it here. Okay, so the difference between the bulk SPR and localized SPR is the surface plasmon wave in localized SPR didn't propagate. All right, so it occupies the surface of the nanosphere. But in this case, because it's 2D thin film, so we have this contour of propagation of the surface plasmon wave. Usually it is called it is actually a bulk surface plasmon resonance, but usually they just call it as an SPR, normal SPR. So we have two types of SPR. The first is surface plasmon resonance, the normal SPR by using thin film. If you use nanosphere or nanoparticle, which the diameter is much smaller than the wavelength of the light, so we will end up with the localized surface plasmon resonance. We'll talk about the resonance condition of it, how in which condition that resonance can happen in each of these cases after this. All right. So hopefully that's clear about the two types of SPR. Okay. So because of this, we can achieve the changes. We can achieve the color changes of metallic nanoparticles from the color of gold that we know, gold nuggets. Okay, this is a picture of gold nuggets. It has that gold color. We are used to the gold color. But when we make it into a nanosphere with the size less than 100 nanometer, we will actually move the plasma frequency towards the visible range. And what will happen is the electron inside on the nanoparticle will start to absorb the light. Right, the light will start to be absorbed at certain region. But in this case, the part of the light that is being absorbed by this gold nanoparticle, the liquid in the bottle, all is nanoparticle with different size. You can see the label 30 nanometer, 40 nanometer, 50, 60, 70, 80, and 90 nanometer. And it has slightly different color between all of these, which I will explain to you why. All right, so if we look at the absorption spectrum of gold now, in bulk gold, the absorption is very minimal. We discussed that already before in the bulk gold. All right, this is the bulk gold, BULK, bulk gold. But when we make it into nanosphere or nanoparticles, the absorption start to increase, especially in the green, all right, and the blue parts. You can see this. Let me draw it. So this is the blue part. We have absorption now, and we also have absorption in the blue. So back to the concept of perceived light. The light is the perceived light is the perceived color is whatever except what is absorbed, right? So now what is absorbed is blue and green. So we check in the table here. If blue and green is being here, blue and green is being absorbed, we will end up with red, right? So the absorption occurs in the green and also blue. That's why the apparent color become red now. That's why we can see all of these liquid nanoparticle is red in color. And the same goes with silver. Silver is very shiny. It doesn't absorb light too much. It's very little. And when you make it into nano silver, it starts to absorb in the region of 400 to 450 region. So so now the white light, from the white light we minus the blue region. So referring back to this table, so we begin with the white light, and the blue part of it is being absorbed. All right, so what we end up with, yellow. So that's why the color of silver nanoparticle is yellow, because of the absorption in the blue region of the spectrum. So another thing which is we need to discuss at this point is the absorbance. It depends on the size of nanoparticle, right? So so basically, when the size, the diameter of the particle it become bigger, the absorbance shift towards the longer wavelength, right? The absorbance will shift towards the longer wavelength. And not just gold and silver. It is not just limited to gold and silver. There's a lot more metal that can have these properties. For example, gold, platinum, palladium, aluminium, copper, and so on. Right. So, but the most commonly used for SPR biosensor is just these two: gold or silver, or the combination of the two. So that is the basic behind the color changes. And actually, when we change the shape of the nanoparticle, this is sphere, we make it into a higher aspect ratio particle. You can see here the length is increasing, right? The length of the particle is increasing. So basically, we are increasing. We have the increasing aspect ratio of gold nanoparticle. So the effect you can see from here, the color also change. And also, it depends on the refractive index of the surrounding. If you put this gold nanoparticle in different solvent with different refractive index, all right, this solvent is actually a dielectric. It's just a dielectric material. You change the refractive index of the dielectric material, you end up with a different absorbance surface plasmon resonance wavelength or frequency. All right, so the frequency will be changed when you put in different media or different solvent. To explain this, we need to go back to this concept. Okay, so this concept. So we change the media just now, we change the solvent. What we change is actually we change the dielectric material. We change the dielectric material, and that actually it affect the surface plasmon resonance. It affect the resonant condition. Okay, it affect the resonant condition because of the surface plasmon wave. Surface plasmon polariton wave, they propagate along the surface between the metal and dielectric. So you change the dielectric properties, the resonant condition also change. All right. So this SPR effect actually has been found in artifacts, in ancient artifacts. This is just addition information. It's not related to biosensor at all. But this is just I like to share with you. Maybe you can have thought your own thought about this. We have found the use of gold nanoparticle or the use of SPR effect on the ancient artifacts. For example, in Islamic civilization, we have found ceramic metallic lusterware. This is actually the ceramic that has different color to it, different pattern. And that pattern, the color of that pattern is actually comes from the nanoparticles that they put inside the ceramic. And we also found this on the in the time of Renaissance in Italy. Okay, some pottery we saw this pottery that have copper and silver nanoparticles, so that it has this different color. And we saw this on the cathedral glass, all right, different color because of this. The yellow glass is because of the silver nanoparticle, and the green, the red glass is because of the introduction of the gold nanoparticle. And we can mix up the two, gold and silver, or we can add up some copper to change the color. So in the end, we can do the color, we can play around with the color how we want. And it's also observed in the Localized cup in British. This is the Localized cup in the British. So if you can see the person on the side of the cup here, right? You can see a person right here. This is actually King Localized. And it is very remarkable that we can see the change of red color in the body of the king and also the rest of the wall of the cup. So the reason for this is they actually purposely, intentionally put more gold nanoparticle on that part of the king body so that it appears differently. So I think it's very if you check in the paper or some talk about this in nanotechnology, they said all of this is unintentional. So that means they do the processing and it is all unintentional. But I believe this is the ancient people, they know some knowledge that we don't know. Maybe the knowledge has been lost, I'm not sure. But this has been found, and not just this, actually a lot more trace of nanotechnology that has been used in ancient civilization. All right, so this is the second part of the talk. Let me check the time. Hopefully I'm not too slow. Oh, all right. So now we talk about the fundamental of the sensing, how the resonant condition in SPR can be met. So the condition of SPR, the surface plasmon resonance, when the SPR will happen, all right? So the SPR will only happen when the wave vector value of the surface plasmon wave is identical to the propagation constant of the incident light. So the incident light is the light that we excite, that we shine the metal, right? And the SPR will only happen if the wave vector of the component of the incident light and also the SPP, the surface plasmon wave, is equal. You can see from here, because this is the dispersion relation, this graph. This is dispersion relation, all right? So the condition for SPR to occur is when we have overlapping between these is the dispersion relation or the wave vector of the photon or the incoming photon, and the red graph is actually the surface plasmon wave vector. So in this, depend on this graph, we can see the overlapping, right? So the overlapping between the photon in the dielectric and the surface plasmon polariton dispersion, and that is where the surface plasmon resonance occur, right? So the reason behind this is because if you go back into the concept just now, we actually have photon to plasmon conversion, right? The photon is being absorbed by and turned into plasmon. But when we see the momentum conservation is not conserved in this process, this conversion process. So to make it so that it's conserved the momentum, so we need to have we need to do some the adaptive optics to the system of the sensing. All right, so this is the photon in air. Let me, okay, so this is the photon in air, the black line here. So that's the wave vector of photon in air, and based on this photon in air, we don't see any overlapping between this wave vector and also the surface plasmon resonance. right? We don't see that because the momentum is less than the SPP, surface plasmon wave. So what we need to do is we need to introduce a dielectric media. Okay, we introduce a dielectric media so that the photon that we launch will go through the dielectric media first before it hits the metal. All right, that's why in surface plasmon resonant biosensor we always have this prism. All right, whether it's a triangle prism or it's hemispheric prism, we need to have this prism for the surface plasmon resonance to occur because of this effect just now. Again, I reiterate this the importance of optical prism to excite the SPR is because the photon will be converted into plasmon wave, right? That's the process of in the SPR. But according to the conservation of momentum, it's not the momentum is not conserved. So what we need to do is we need to increase the momentum of the incoming photon, and the way we do that is by adding a dielectric material with high refractive index on top of the surface of the metal, so that the wavelength of the light will be shorter. We know when light travels in the higher refractive index, the wavelength will be shorter, right? Because of the wavelength is short, we know the momentum is high. P is equal to h divided by lambda. P is the momentum. H is the Planck constant divided by lambda. So when lambda is very small, the P is the momentum is high. So that's why the curve, the line here for the photon in dielectric the slope will reduce. And in this case, after the slope has reduced, now we have the resonant condition represented by the overlapping between the surface plasmon wave vector and also the photon, the incoming photon wave vector. All right, so when this surface plasmon resonance occur, we need to characterize the evanescent field in that occur. Okay, so consider this is the where the SPR occur. Okay, we have this surface plasmon resonance, surface plasmon propagation along the surface of the metal. We have discussed this, and part of the wave, actually, part of the surface plasmon wave is being converted or leaked inside the metal in the form of evanescent field. Okay, this is a concept in photonics, in optics. So some of the power of the surface plasmon is actually being penetrated or lost or leaked into the metal, but most of the surface plasmon field is actually being probed into the dielectric. Okay, you can see this red graph here. So, all right, so we have huge evanescent field and far long range evanescent field into the dielectric. So you can imagine by now that is how we use this as a sensor, because of the field, the surface plasmon field that travel along the surface of metal and dielectric. It has the evanescent field that emanates from the surface up to a certain distance. Right, so that is the called evanescent field in the dielectric. So since the dielectric is what we want to change, right, the dielectric is what we want our measurement in terms of sensor, we call it the measurement, what we want to measure. So we change the dielectric material, so in the end the evanescent field will change. We can detect that through the surface plasmon resonance condition after this phenomena. All right, so let's consider the wavelength of light that we introduce to the metal surface is 500 nanometer, and the evanescence wave into the metal is very short, just 5 nanometer, because we know metal, the metal have very high refractive index, so that's why the refractive index, the penetration is very low. The evanescence wave or the penetration depth into the dielectric is very large, very long, right? 250 up to 1 micron. So our surface of metal just now, it can sense whatever dielectric material that we have from 250 nanometer up to 1000 nanometer. It depends on the wavelength and depends on the what type of metal and so on. But this is how we probe into the dielectric, right? And the propagation, the propagation of the surface plasmon polariton can go up to 1 millimeter. Then the surface SPP wave that I showed you just now, it can propagate up to 1 millimeter at a certain wavelength and condition. All right. Okay, so this is resonant condition of SPR or bulk SPR. We know it's bulk SPR because we use a thin film of metal, right? We don't use nanoparticle, so that this is called surface plasmon, bulk surface plasmon resonance. And since the penetration depth or the evanescent field towards the dielectric into the dielectric is very long, it's between 250 up to 1000. The maximum evanescent field length is up to 250 nanometer until 1000 nanometer, which is 1 micron. So therefore, it's very sensitive towards the change of the medium. All right. For example, this is the thin metal just now, and this is the dielectric. Remember, we need the dielectric for the SPR to occur. Okay. We need the dielectric. So it's very sensitive towards the slight changes in this region, in this dielectric region. For example, we have solution with different concentration, right? You introduce solution first with the lowest concentration, and what we'll have is the evanescent field will react with the dielectric media, and because of that, the resonant condition will change, and we can detect them. We can detect the change in our setup. And it is suitable for bulk RI sensing because of far range. Okay, if you want to change, you want to measure the refractive index of liquid, for example, this is very suitable by using this SPR because of far range of the evanescent field into the dielectric. And it's also suitable for large bioentity, for example, cells and so on. All right, so yeah, large bioentity, cell and tissue and so on. And the second type of SPR, which is called localized surface plasmon resonance, the condition that is happen is the lateral dimension of the interface here. Before we talk about this surface plasmon resonance, surface plasmon propagation, right? And in the thin film, it can go up to 1 millimeter. It can go up to 1 millimeter. But for a nanosphere, if the size of the nanosphere is much less than the propagation length of the surface plasmon resonance, then we have the localized surface plasmon resonance. So basically, like I mentioned, the surface plasmon resonance didn't propagate. So that's why it's called localized. The condition for this LSPR to occur is the light that we introduce must have the same frequency with the natural frequency of the oscillation in the nanosphere. So this is a nanoparticle. Like I mentioned, it has the free electron and it oscillates, right? It oscillates at a natural frequency by its own. But when the natural frequency is equal to, or when we introduce light with the frequency similar to the natural frequency of the oscillation, we know that the oscillation will be the amplitude of the oscillation will be higher because of the resonance, and that creates the LSPR phenomena. This LSPR phenomena can also be used for sensing, but if you can, I think you can imagine by now, because of the evanescent field is much shorter compared to the SPR just now. So the evanescent field into the dielectric, is much shorter in this case. So therefore, we have minimal effect on the bulk effect, right? So what it is sensitive to is only at the surface of the metal film. All right, so the dielectric, the length of the evanescent field, the maximum length of the evanescent field into the dielectric is up to 20 nanometer until 40 nanometer. So it's very short compared to just now. All right, it's very short. So therefore, it's very sensitive only at the change of the refractive index at the vicinity of the surface of the metal. All right, so this type of LSPR is suitable for biomolecule binding detection because short range. So biomolecule is very small. It is in a few nanometer size. So therefore, by using LSPR, it might not be what we call it, be sensitive. It can be sensitive, but we have the bulk effect just now, which we want to avoid. So we can use LSPR for detecting small biomolecule binding. Right. I can't see the titles. All right. So SPR biosensor is a label-free detection method and very reliable method in clinical analysis for biomolecular interaction. So it is a label-free detection method because we don't need a label. We don't need a reporter tag such as a biotin, radioisotope, fluorophore, or enzyme to get to the target biomolecule. So basically, it is a label-free. You introduce the sample, you get the result. You don't need to put something into the sample. All right. Nowadays, in medical application, they need some of the sensing they need to do to introduce the radioisotope into your body, for example, right? So based on the radiation from the radioisotope that you eat inside your that has been inside your that are inside your body, so they can trace or they can probe the changes in that reaction. But in this case, we don't need that labeling or reporter tag. It's a label-free detection because we coat the metal surface in SPR sensor with a specific analytes, specific ligands that will interact with the biomolecules, right? And it make it possible to measure the interaction in real time with high sensitivity. So this is also another important advantage of SPR biosensor because we can do it in real time. All right, even we can know when the two biomolecules they start to bind and unbind. We can monitor that over the time. So it's capable of detecting binding of macromolecules such as protein and DNA, enzyme and substrate or inhibitor, receptor, drug, lipid membrane, protein polysaccharide, cell, virus with protein, and etc. So this the binding between the molecules that we want to detect by using our SPR biosensor. So what information that we can get from the biosensor, from the SPR biosensor, we can know whether the binding occurs or not, right? Specificity is whether it's specific to a certain the binding, affinity, the association and dissociation. We can know the kinetics of the binding. If we take the result over the time, we can know the kinetics. And last but not least, we can know the concentration of the samples that we introduce into the sensing region. So the principle is it measures the refractive index changes in the vicinity of thin metal layer in response to biomolecular interaction. So what is in the blue here, the triangle, the almost triangle blue shape here is actually represent the evanescent wave that propagates or that emanates into the dielectric. So this is the evanescent field. This evanescent field is what what makes the SPR is very sensitive towards the change at the surface of the metal. All right. So for example, we have interaction between the two biomolecules at the surface of the metal. Even few binding of the biomolecules can already being detected by biosensor because of the refractive index start to change, right? The refractive index at the surface start to change, so the SPR sensor can detect that. So in SPR biosensor, probe molecules are firstly immobilized onto the sensor surface. So this Y shape is the probe molecules, what we want to the biomolecule, the target biomolecules to bind with. Right, this is our probe molecules. We code with this, and after that we introduce the target biomolecules. This is the red one, and we know the binding will occur, and that binding will be the binding will affect on the SPR condition, and in the end we can see in the SPR signal. So the A, which is without the biomolecules, the interaction of biomolecules, the result is blue. It's no analyte. And when we introduce the biomolecules, the analytes, we can see a shift in the SPR signal because of the resonance condition has changed. The resonance condition has changed because the refractive index at the surface layer of the metal, at the thin surface layer, a surface interface between the metal and dielectric has changed. So different SPR condition, that is what we detect in our SPR sensor. Okay, so now we talk about the configuration, different configuration. The first is in this configuration, the key important thing is we want to achieve high performance. And how we achieve that is we aim to have optimal coupling between the excitation light and SP wave vector. So excitation light is the photon, and the phase plasmon wave vector is the plasmon wave. So we want to have this efficient coupling between the photon and also the plasmon polariton wave. So to do that, we need to consider that's why we need to consider the configuration of this sensor. How we want to measure, all right, how the change in the refractive index can be measured in our instrument. So the first technique is by using surface plasmon prism coupler. This I have discussed just now. We add a glass is actually to change the momentum of the light, all right, so that it overlap with the dispersion relation or the wave vector of the resonant of the surface plasmon, all right. So this is, for example, this blue is without the glass, without the prism. So we don't have the surface plasmon resonance because no overlapping with the red one. Once you introduce the glass, so the light will pass through the glass first. When the light pass through the glass, we know the glass has higher refractive index compared to the air. So the wavelength will become reduced. Once the wavelength is reduced, the momentum is increased, right? The momentum is increased. So in this case, now we have overlapping between the two. We have the resonant condition. We have the resonant condition. So this configuration is called, the configuration A is called Crashman configuration. This is actually the most common configuration of SPR sensor. So most of the sensor actually using this. So the sample is here. You can see here. In the channel, it can be liquid. All right. So we introduce a liquid into the channel. So this is what the area of the dielectric that we are sensing. We sense electric. Okay, I cannot write properly. So this is the dielectric, and this is where we excite the surface plasmon. All right. This is the light, the incoming light. This is where the surface plasmon start to form, and it will propagate along this up to here. All right, because the surface plasmon resonance, the surface plasmon propagation can be very long, can be up to a few millimeters, right? So in this case, this is what we have here is the evanescence wave in this region. All right, the evanescence wave. So the evanescence wave acts as a probe into the sample, so that changing the sample will have different evanescence wave, and the resonance condition will change. So we'll have different signal here. So that's the Crashman configuration. And the second configuration that also equally popular, but not as much as Crashman, is auto. Is by auto, this is B. So the difference between the two is the excitation is actually happening. The sample is actually in between the metal and also the dielectric, right? So the metal and the dielectric. So just different configuration for different applications. Certain application they need to use the auto, but most of the application they need to use Crashman configuration, right? All right, you can read here. It has become a standard technique to excite the surface plasmon in regards to its alignment simplicity, leading to easily controlled parameter and variables. The underlying principle of this is to conduct the excitation of surface plasmon using transverse magnetic field wave to the smooth metal sensing nanofilm through a high RI prism. Okay, so this is a high refractive index prism. Again, it is required so that the conversion between the photon and plasmon propagation and plasmon wave, surface plasmon, obeys the conservation of momentum. All right. So this is the Spr incident angle. If the Spr will start to occur at certain angle, right? This theta here, all right, it only occurs at certain angle, and this angle, how we can measure this angle is by changing the angle of the detector. So this is our light source. This need to be our detector, and we need to change the angle of the detector so that we can find we can change the light also, the light source angle also, the incident light. But in the end, we want to find what is the angle of the SPR, of the occurrence of the SPR. So the theta can be given as this equation. This is the end of the prism, the refractive index of the prism. So the prism actually is very important. It's not just there. It serves a purpose to be there. It's very important to be in this setup. And this is the dielectric constant, the real part of the metal, and this is the real part of the dielectric constant of the dielectric. So it will be this is what changed when we introduce different sample. The dielectric constant of that sample will change. All right, dielectric constant is same to refractive index. Okay, so once the dielectric constant change, the refractive index will change. So therefore, the whole theta will change. All right, that's the first configuration. The second is this is the little bit old technique is by SP grating coupler. Okay, in this case, we don't need to use prism so that we have overlapping between the wave vector of the incident photon and also the surface plasmon wave. But what we do is we make the metal looks like a grating. Okay, the surface of the metal as a grating, and because of the incident light hits the metal at different angle, right? So we have the diffraction at a certain order. We have different order, and one of the order or because we have a lot of order. Okay, one of the order might coincide or overlap with the surface plasmon wave vector, and it creates a resonant condition. So this theta b is the propagation constant shifting in the presence of the grating, which is not present in the prism coupling configuration. So by having this grating, we can have different of incident angle, and by having that, we can have this resonant condition. So at the resonant condition, you can imagine that most of the light is being absorbed, all right, because the photon has converted into surface plasmon. So therefore, the amount of light that is reflected is very less. So that's why you can see a dip in the signal, right? The signal reduced at certain angle or wavelength. We'll talk about that after this, because of the photon now has been absorbed and converted into surface plasmon wave. And this is the resonant condition for this grating coupler. You see, it depends on the grating properties and also the wavelength and so on. But this is what changed in the equation. We change the sample, we change the dielectric, the dielectric constant of the surrounding. So therefore, the resonant condition change. The third configuration is by using a waveguide. Maybe I need to go quickly because I have 10 more minutes, I believe. So waveguide, the advantage of using waveguide is we need to use polychromatic light, which is light, the broad light source. We can use laser, And waveguide provide the option for monetization. That's the advantage of waveguide. And the disadvantage of using waveguide is because of the limited sensitivity due to the limited numerical aperture for waveguide. Because we cannot change the angle, right? Yeah, and secondly, it's not non-adjustable angle. And this waveguide can be in a planar substrate. All right. So what happens is we have this waveguide. All right. This guided mode is in the waveguide of light. We coat the waveguide on top of it with a metal film to induce the surface plasmon resonance. And we have this media, dielectric media, that this is the sensing, our sample or sensing media or measurement. Right. So the same concept applies. The resonance condition will change if you change the sample. So the same, but instead of in the bulk system, we can do it on top of a planar waveguide. And this also can be done on the optical fiber. All right, optical fiber. So the light that we pump comes in from the input of the fiber, and in certain parts of the fiber optics, we reduce the cladding and we replace with the metal film. So we want to induce SPR effect. So all the things, the phenomena or the mechanism is the same. Just we change how the configuration of the detection. All right, but using the optical fiber is actually very good. Has its own advantage because now the metal film is actually covers the whole waveguide. It's very it can be very sensitive because the metal film, it covers all angle, and we don't need to specify certain polarization in incident light. So it can be TE or TM because it's cylindrical, and all the interaction occur all at the surface. Or I mentioned here large sensing area. So the sensing area is very large because it is a cylindrical compared to plain or planar film of metal. The fourth configuration is localized surface plasmon. All right, localized surface plasmon resonance. This is another configuration. Here we don't need to use any angle because this is no longer a thin film. We don't use metal thin film. This one we use nanoparticles. All right, so nanoparticle will produce localized SPR or LSPR. So what we need to do is we need to have a light source. We need to have the same. We need to have a substrate. So that this will be our sample, and these are our nanoparticles. And what we detect is actually the absorbance of the whole setup. So this can be very easy to do. But in terms of the equation, it's quite long. This is what we detect: the dielectric change of the sample, the dielectric constant of the sample, and it depends on the lambda and so on. Okay. So this technique is based on transmission attenuation configuration. So basically, it's just like a absorbance, normal absorbance detection. This is a few methodologies of SPR biosensor, of how we collect the data. All right. So the first is we by intensity modulation at particular wavelength or angle. So in this case, we don't need to change the angle. We just monitor the intensity modulation. So we introduce different sample. We monitor the intensity of the reflected light. All right, we don't need to change anything. There's nothing moving in this first methodology. We just monitor the intensity, how the intensity changes with different sample. And the second is incident angle interrogation. This usually we use a monochromatic light to excite the surface plasmon. You know, monochromatic light is laser, a single wavelength. We use laser. So in this case, we need to change the incident angle. Change the incident angle until we found the minimum point of the intensity. So this is the same 1, 2, 3 referring to the same graph here, right? Okay, so in number 2 we change the angle until we found a dip in the intensity. So we change the angle in the second methodology. The third methodology, we start with not a laser, we start with a broadband light source. It can be a polychromatic light source. One of it is can be LED, it can be a halogen lamp, and so on. But in this case, we need spectrometer because we want to find what is the dip in the wavelength, right? What is the dip in the wavelength? Because in the surface plasmon, it occurs at the specific wavelength, So we want to know what is the absorption, where is the absorption of the surface plasmon absorption occurs. Okay, so basically the graph will look the same, whether we use theta or lambda. Okay, the fourth is the phase interrogation. This is less reported in literature because it's more complicated and require phase shift equipment. This little bit different, complex. It needs a lock-in amplifier, and that's why it's less popular. Right? I remember I used lock-in amplifier in 2012 with Dr. Yassin, with Prof. Yassin. I learned how to use the lock-in amplifier with him before. So that's why when I read about this, I start to think, it makes me remember about the lock-in amplifier. All right, so we can also do all this measurement or signal acquisition with real time. That means we measure the intensity over time, so we can see the kinetic of it when the RI of the sample start to change and so on. All right, so this is another advantage of using the SPR, real time measurement. So I think we have few more, 5 minutes. Let's look at the important application of SPR biosensor. I'm not going too detail on it, just a little bit that I found in the literature. So most of them, they use SPR biosensors for biomedical application, mainly for interaction analysis. So to study interaction between the biomolecules, they usually use SPR biosensor. And it also has been used for mutation detection. Okay, so mutation in the protein molecules, to detect that, we can use this SPR biosensor. Or we can do the conformal change studies, structural change of protein molecule. The protein structure molecule, if the structure change, we can also detect them, the changes in the SPR biosensor. All right, so it can also be used for proteomics researchers. For example, is tumor-associated DNA marker. With the combination of surface hybridization, ligation, and nanoparticle amplification for early detection of breast cancer. Okay, this can also be used. So basically, what we change in all of this application is we change the pair. All right, the analytes and also the binding, the biomarker, the probe molecules that we introduce on the surface of the thin metal film. And also this is related to protein biomarkers, detection of small concentration of important biomarkers in blood samples. All right, because this is very sensitive, we can use this to detect even small concentration biomarkers especially in biomarkers in blood sample. We can use SPR biosensor as a high throughput screening, for example, mostly on the drug delivery or drug development, when we want to test the drug efficiency and so on. I'm not well versed in these topics, but basically we want to test the interaction of or the efficiency of drug and so on. We need to measure a lot of samples. All right, so by using the SPR biosensor, we can do this high throughput screening. We can just fill in the samples and the sensor will detect it. And last but not least is the cellular analysis and detection. We can monitor the cellular response, cellular addition, cellular products, cancer cell detection. So in the cellular analysis and detection, we can use the SPR, the bulk SPR phenomena, because of the farther range of the evanescent field. But it's not limited to that. We have also other biosensor application based on the bacteria detection. We can detect the bacteria, or we can use this for environmental monitoring. It is also part of biosensor because we use biomolecules, but it's not in the application of biomedical. We use biomolecules to do the environmental monitoring, for example, and so on. And this SPR biosensor has found its own market. There's a lot of commercial SPR biosensor that are readily available. So the key important things between these products is miniaturization. All right, some are big, some are small. And Liu et al., it is one paper that I found, they make it into smartphone in 2015. So the sensor is actually, they use the light source from the LED, so that means it's a polychromatic light source, and they use the camera as the sensor for the SPR biosensor. And I tried this, one of my master student, he do this on a smartphone, and we managed to detect detect the change in refractive index, but not for biosensor. We do it for salt salinity sensor, right? So we use the light source that comes from the flash of the smartphone and the camera as the detector. So it can be very small, and it can be very, very cheap. This is what I want to share with you. I think this is the last thing. With related to the current pandemic, the SPR biosensor has been mentioned a lot when you Google for SARS COVID detection or something, you will come across the word surface plasmon resonant biosensor. So there are different types of recognition agent or based biosensor and virus target. We can use the antibody aptamer peptides, antibody or aptamer or peptides to detect the virus. All right, so the virus will attach to the antibody or aptamer. So that will change the refractive index at the vicinity of the surface, and therefore we can have the different surface plasmon resonant condition. And in B, we can have it DNA, complementary virus DNA, and also the DNA from peptide. And the third is we can, this is the other way around, we can immobilize the virus antigen on this metal surface, and the sample is the virus, the antibody compared to the A just now. This is the other way around. We can have these macro molecules between the strongly bound healthy cell and weakly bound viral infected cell. We can have that binding, or we can have this molecularly imprinted polymer. So basically the virus will only bind into a specific binding sites that we have prepared on top of our gold thin film. So in the end, when the virus binds to the sites, we have different in the refractive index, and we can detect that. And there are few papers, for example, in 2020, they use for this current COVID, the recent paper 2020. So they use SPR to study the binding kinetic analysis of this virus, coronavirus. In 2009, they used the same, but for the SARS, right, in 2002, I believe, we have almost same virus like this COVID. So they use the SPR sensor also. And all right, and also we have this LSPR. Some of it also use the localized surface plasmon resonant. And between surface plasmon resonant and localized surface plasmon resonant, when we want to choose which one, we need to look at the application. All right, what kind of application, what kind of biomolecules that we want to detect. So we need to choose, so that after that we can choose whether we want to we want to continue with the LSPR or surface plasmon resonant. So basically, whether we want to use nanoparticles of metal, or we want to use a thin film of metal. Or in summary, the surface plasmon resonance technique has been proven to be one of the most versatile framework for biosensor application. It provides excellent analytical performance in terms of sensitivity, fast response, the limit of detection, reproducibility with its label-free and real-time approach. This is very important advantage compared to label types of diagnosis. Typical detection limit is 10 picogram per mil, is very, very small. And it can be make it into a very portable and handheld device. And it can be very low in cost because we don't need to use very thick gold. It's very thin, of 46 nanometer of gold for SPR. For LSPR, we can use like 10 nanometer of nanosphere. And the commercial SPR has been there in the market, but most of them, they use the prism coupling technique. Remember, I mentioned, I discussed about the four configuration, and most of them, they use based on the prism coupling, especially the Crashman configuration. And the LSPR biosensor provide much more sensitivity to changes in the bulk. I think this is the other way around. Let me change it. So this one should be SPR, not SPR. So SPR biosensor provide much. Sorry, this is correct. LSPR biosensor provide much more lower in sensitivity changes in the bulk refractive index because of the evanescent field. Right, the maximum range of the evanescent field is much shorter, so it is not sensitive towards bulk changes in the dielectric media. But LSPR biosensor can be powerfully complementary for SPR biosensor. So that, like I mentioned, some of the application we need to use SPR, some of the application we use LSPR compared to SPR. That's all from me, I think. I have exceed 5 minutes. Sorry about that. So maybe I can open for question and answer. Prof.
Thank you very much, Dr. Munzir.
All
That
right.
is very interesting presentation. Wonderful, Dr. Munzir. It's a very new experiences for us. Yeah. Okay, we can continue with the question and answer. Please, if you have anything problem or anything understanding, please kindly raise your hand and please deliver your question. Okay, time for yours. I want to all of you as turn on your camera. I want to know, are you healthy, all of you? Okay, it's very pretty and wonderful voice. Okay, any question? Thank you very much for
maybe if you don't want to ask, you can type your question in the chat box. I can read from
if
here.
you can. Yes, or maybe you can direct question for Dr. Munzir.
Yeah, can also. Maybe I can start with my question. I can ask all of you to begin with.
Okay.
Anyone of among the students, why we don't have this surface plasmon resonance for semiconductor material? Anyone want to answer? Why we only have this surface plasmon resonance for metal? Why don't we observe this for other semiconductor material or any other insulator? Anyone want to try?
Come on.
I want to try.
All right.
Maybe because of the free electron in metal, but in the semiconductor is not only not free electron. Maybe.
Yes, very correct. Very wonderful answer. Yes, it's correct, because we have bounded electron in the semiconductor, because we have the valence band and we have the conduction band. So that gap of energy is actually creates there's no free electron. Basically, there's no conduction band free electron in the semiconductor. So therefore, there's no plasma. So there's no plasmon. Right, so that's why only metal has that plasmonic properties. All right. Any question from all of you? We have like a lot of time actually. We still have.
Maybe I will.
All right. Good answer just now, by the way. Imasda, right?
Yes, I want to ask about
Yeah.
two questions for me.
Okay.
The first one is, maybe Dr. Mujir can explain again the main points about how biomolecular samples can change the light output through the SPR principle. And the second one is, if I want to detect biomolecular like fungi that contain aflatoxin, I detect on fiber optic sensor and SPR, what will the working principle be like to detect biomolecular concentration and the figure of the output?
Right.
Yes.
The first question about I think I need to share again my slide. How to share here? Let me find the suitable slide to start with. All right, let's look at this slide. Okay, so in the surface plasmon SPR biosensor, I cannot, never mind. We are detecting the reflected light. Okay, we are detecting the reflected light. So this is the incoming light from the light source. This is the incoming light. Okay, so we know in the surface plasmon resonance, some of this photon or most of this photon will be converted into the surface plasmon wave. All right, at this surface, at the surface of the metal and also the dielectric, we will have the conversion from the photon into the surface plasmon wave. And that conversion is actually can be detected by the output or the reflected light. For example, here we have 100, for example, 1 watt. Let's put it as a percentage. For example, we have 100% of light that comes in, the incident light. And at this process here, surface plasmon resonance, 80% of it has been converted into surface plasmon resonance. And what is left from the 80% is 20% only is being reflected at exactly that angle. Okay, what angle is, if you ask me what angle, the angle is this angle. All right, the sine theta angle, and you can calculate by using this equation. And the theta is depends on the dielectric constant ED. This one, I think epsilon maybe, small epsilon of D. Dielectric is the sample. I mentioned just now. The dielectric referring to the sample, the medium, sample medium. And when you change the sample, the dielectric constant of the sample will change. All right, so therefore the whole equation will change. The theta will also change. The angle of this will change. For example, the first one occur at 46 degree. Okay, when you introduce your sample, it no longer occur on 46 degree. The SPR just now angle, it occurs at 50 degrees. 50 degree. So if you plot the graph, that's why we will end up with this. All right. So as we change the angle, there will be one particular resonant condition whereby we have most of the light is being absorbed. All right, at this position, well, just now 80% of the light is being absorbed before it is reflected, before the resonant condition start to disappear. All right, so that's why we monitor the reflection of the light that we introduce to excite the surface plasmon resonance. That is on the grating. That's on the prism coupler technique or the Crashman. This is the Crashman technique. But if you do it on the fiber optics, I believe this is your second question. You want to do it on fiber optics, right? So in your fiber optics, you can do this same like this configuration, all right? But instead of a single wavelength, you need to introduce polychromatic light. You need to introduce broadband white light source. So what happened is you have all the wavelength, right? At particular wavelength, this is, for example, this is the graph of your. It is impossible to be like this, but for simplicity, I just draw like this. This is your input spectrum. This wavelength, this intensity, right? So when the light passes through this sensing region, whereby you have coated with a metal film, resonance will occur at certain wavelength. So therefore, the output of the light you will end up with at absorption at certain region of the transmitted light, right? So part of it has been absorbed, and that is what I show you here. So the same deep trend, we call it deep trend, it can occur at a wavelength, different wavelength, and can occur at different theta. All right. But if you change the angle incident angle, right? You change the incident angle, you need to use laser, right? Because if you use white light source, it is not coherent, right? It's not directional. So you cannot point the light from LED into one position, right? You need to use laser for the change of angle. So for the change of angle, you need to use laser. But if you use polychromatic light, you need to integrate with the spectrometer so that you can have this the same deep, but instead of theta, you change it is measured over the change in the wavelength. Hopefully I answer your question. But your answer, you asked about the biomolecules interaction, right? So you mentioned about vaccine something. So what you need to do is you need to functionalize this surface of this thin film with biomarker or probe molecules that can detect the molecules that you want. All right, for example, you want to detect DNA, so you need to functionalize, or you need to immobilize certain type of probe molecules in the surface, so that it becomes very sensitive. If you just want to find the concentration, or you want to detect the concentration change, you don't need to immobilize, or you don't need to concentrate, you don't need to functionalize or immobilize with anything, because I mentioned just now, the evanescent field will travel up to 1 millimeter. 1 millimeter. So it's very long. It can sense the refractive index change of the surrounding. You change the concentration of liquid, definitely your refractive index will change. All right. All right. I hope.
Okay.
Your question.
Thank you, Dr. Munzir. I got the point.
Okay. Any other question?
Thank you. Question? Hello? Another question? Yes.
Anyone?
Ahmad Fanani, do you want to ask something?
Yes, Prof.
Okay, please.
Okay, thank you, Dr. Mundir. I have one question. Which are better, localized SPR or bulk SPR? Or it will be depend on what we want to measure, because we know that many bioactivity will have different characteristics. Thank you.
Can you repeat your question? I can't really.
Which are better, localized SPR or bulk SPR, or it will be depend on what we want to measure?
Yeah, it depends on what you want to measure. if your biomolecules or bioentity is big, like cell, right? Cell is big, is in a micron scale. So you need to use SPR. You cannot use LSPR because of the evanescent field in the LSPR very short. So it will not be sensitive to that. If you want to detect a very small a protein structure, which is a few nanometer across, protein structure can be complex, but maybe the size, the diameter of it can be a few nanometer across. And if you use SPR for that, it might not be sensitive towards the slight change in the concentration, change in the sample. So therefore, you need to use LSPR for that, right? So you need to check your application, and you need to tune so that it can perform the best, right? I haven't actually, there's more technique on how to improve the sensitivity. One of it is on top of the thin gold layer, you add another layer. For example, you add more nanoparticles and so on. So this is actually we do modification so that the interaction that we want to happen will happen on the sensor, all right, in our sensing region. So it is not actually a similar setup. If you want, you go to the literature, you check the paper. If they want to detect different biomolecules for different application, the setup might be different. Maybe they add more layers and so on with a specific aim to detect maybe a specific type of biomolecules. That's what I think I can answer.
Okay, that's clear. Thank you, Dr. Mundir.
Right.
Another question? Yes. Okay, maybe I want to give some question for you, Dr. Mundir.
Yep.
Actually, we have to do some experience about the SPR. We use the photodynamic therapy. We use the gold nano rod for the inactivation of cancer, breast cancer. But actually, we don't have the instrument for the real-time measuring. We use the biological and chemistry analytical for to know whether SPR is really occur in this phenomenon. We use photothermal mechanism and photochemistry mechanism. Actually, the result of the interaction, they are using the inactivation of cancer cell. But I don't publish my result of research because I still some explanation about how the physical phenomenon. Maybe the next time we can do the collaboration for the maybe to give some explanation for the physical area, because my result, the answer is the chemistry and biological result, but I want to know the how is there are some solution. How about this, Dr. Mundir? Because I think we can maybe we can make some collaboration of research and joint publication for this. Maybe I can want to make in English. Maybe I can send you. Maybe we can give some improvement about the physical phenomenon for the improve this article. I think like this.
Inshallah, I will try. Inshallah, because I don't have the experience for the PDT, photodynamic therapy, but one of my colleagues during my PhD time, they're working on the PDT by using gold and silver nanoparticle for the cancer.
Oh, okay. And USM?
SM, I'm not sure. I'm not sure. Maybe this one, I'm not sure.
And your colleagues are from where institution?
And before, when I did my PhD, so
Okay.
he's doing for that in that project.
Okay. Actually, I have tried to answer in physical phenomenon, but maybe I'm not believe it. I'm not believe it. And so I want to know about the what's the kind of the instrument to measure of the interaction in real time with high sensitivity. The kind of instrumentation, maybe you can in your laboratory there are instrument also on maybe.
You mean the aspect the equipment?
Yes. For the real time.
I'm not sure. In USM we don't have that actually. I don't know. Maybe we have. I'm not sure. But the one that I plan to have is actually based on the fiber optics. We can do the real time also. Fiber optics, I show you. Fiber optics SPR biosensor. But we can monitor the signal over time also, so we can have the real time measurement of that.
Using what? What equipment?
Fiber optics based SPR.
Oh, okay.
Fiber optics, yeah.
And
UM? UM, I'm not sure. Maybe they have, maybe.
And where they have the equipment?
I'm not sure. Sorry, Prof. I'm not sure. But maybe in UM they have it. Maybe. I'm not sure. Yeah.
Okay. Thank you.
But for the fiber optics, I think we can have it here. We can do the real time monitoring here. So what we need to do is just monitor the change in the wavelength over time, so we can have the real time.
Yes. Okay. Thank you very much. We have 5 minutes again, please. One more question to Dr. Mundir. I don't make some question from the master degree student. Please. Welcome to Dr. Farah Wahida, Laser Center, University Teknologi Malaysia. Welcome to Dr. Bahtiar Musa, Dr. Asnawi, dan Pak Yosef from Universitas Erlangga, Dr. Ahli from Universitas Negeri Surabaya. I don't know, Dr. Bahtiar Musa. Where are you from, Doctor? Maybe you can give some question for Dr. Munzir.
All right. Assalamualaikum. My name is Bahtiar Musa. I am actually lecturer from UiTM Cawangan Terengganu in Dumul, Malaysia. Okay.
Thank you very much. Yeah.
It is actually a very good presentation by Dr. Munzir, and I really enjoy it. Okay. Thank you, Doctor. And also to Prof. Edna for organizing, and USM, right, for organizing the seminar. Thank you again.
Hope it will help a little bit. We share knowledge with one another, because I'm new also into this, but it's interesting for me. So I like to share with others. All right.
Okay, thank you, Dr. Bahtiar Musa. Yeah. Okay, once more again. Question? Renzi? Muhammad Kasaf?
Sorry, Prof. Actually,
yes?
my field, interest of field is really different from this nanomaterials.
Yes, but actually, I think
Yeah, I don't have too much information about nanomaterial. That's why I didn't understand anything. Actually, my background is in computer. That's why.
Okay, thank you.
Okay.
Yes, okay. But I think the explanation from Dr.
Yeah,
Mundir,
it's good. Yeah.
yes, this is the multidiscipline, yeah,
Yeah.
doctor. Not only biophotonics and photonics, maybe
Actually,
also the material photonics. But
yeah,
I, yes,
yeah. My area of interest is in artificial intelligence, like software
okay,
based. Yeah.
yes, thank you. Yeah, okay. Because I think we can must knowledge about the material science to Dr. Mundir, yes, about the condition of the or choose for the metal is the suitable with the goal of our research. I think like this. Okay, another question, Mas Jul.
Masih belum ada tuh.
Arsita? Masih belum ada. Arsita, Wirano? Pak Yosef mungkin? Nggak ada pertanyaan? Oke? Oke. Kalau memang there are no question, I will close. There are 1 minute again for this meeting. Please kindly give the applause for Dr. Mundir for the interesting presentation. So thank you very much, Dr. Mundir, for your time today. I think it's very, very interesting, and maybe we can continue the research collaboration. Thank you very much, Dr. Mundir. Thank you for Dr. Bahtiar Musa, Farah Wahida, Dr. Asnawi, dan Pak Yosef. And so thank you for participation for all student bachelor and magister degree. Once more again, thank you very much. Thank you very much, Dr. Mundir. Assalamualaikum warahmatullahi wabarakatuh.
Thank you. Assalamualaikum.
Waalaikumsalam. Welcome, Dr. Bahtiar Musa.